Okay, good morning. I hope that, or it seems like lots of people are on their way in, but let's start already because we're already a little bit over time, and it's the day after the conference banquet, which is traditionally the day where some people have hangovers. So I came to Star Trek very late, even after becoming a computer scientist, even after my PhD in computer science. I know it's weird. So, but basically, yeah, I know it's weird. So, but basically, so when I so when then I stumbled upon Mito's game, Red Shirt, which is a space social network simulation game where you play as someone on the website Spacebook and will need to avoid being sent on some kind of suicide mission. And I had a lot of fun, probably because I mean, at least partly because I actually remembered everything that the jokes referred to. It's pretty great. It's also a really interesting and original game idea, which is sort of typical of Mito. So Mito is another one of these people which are very hard to sort of pigeonhole because she does a whole lot of things. So our bio on the website starts with that she's a game designer, scholar, and entrepreneur, which is pretty cool, right? So doing game studies, doing game design, and also running her own sort of game AI startup, which is pretty cool. So she basically does almost everything we're interested in here. So she's an assistant art professor here at the NYU Game Center. She runs Spirit.ai, a game development company called The Tiniest Shark, and overall does a whole lot of awesome things. So when we asked her to give a keynote here, we knew that she was going to say something awesome. We don't really know what, but hey, it seems great. And apparently it's about feelings for engineers, and I have feelings for engineers, so take it away.
Okay. So thanks everyone for coming. Thanks Julian for the kind introduction. So I'm going to be talking about feelings for engineers. Now you can either process that with a comma after feelings or not, I guess. There's two ways to understand that. But anyway, so what I want to talk about is how a few years ago I decided to model love in a game I made called Red Shirt, which Julian mentioned. So Red Shirt was a social simulation game about trying to interact with potentially hundreds of generated NPCs on this simulated space station through this mock Facebook, but in space type interface and narrative. And in the game, you're playing as this sort of nobody space janitor type who's trying to climb up the ranks, whether that's through sort of genuine hard work and perseverance or through various Machiavellian, am I not close enough? Or through various Machiavellian antics. So the interface and interactions try as hard as possible to map to the things that you can actually do on something like Facebook. So things like posting statuses, liking other people's statuses, maybe liking your own status, sending private messages, friend requests, updating your relationship status, and so on. And so I decided to write some code for how love might work. What happens when you send a relationship request to someone, or one NPC decides to send a relationship request to another, and how does the other one decide to respond or not? So here it is. You'll have to excuse the horribly inoptimal code. Some of it was rewritten later. But there's a few important variables at play. For example, one of the things that it looked at, and for some reason, one of the first things it checks is, are they already good friends? And the friendship has to be especially strong if they've already dated before and broken up before. Do their preferred sexualities line up? And bearing in mind, in Red Shirt, the default for creating the player character is bisexual. And then there's other things that go in there as well. There's a couple more fluffy items. So there was a romantic tendency variable that each NPC has, which defines how likely it is that they might fall in love at all. And then crucially, there's an essential piece of randomness, of course. So I want to talk about that. Well, firstly, I mean, I'd love to say that there was some deep scientific basis for having chosen to model love in this way. But really, it was entirely anecdotal, based off of both my own experiences at the time and the experiences of my friends and what I was exposed to, and I'm sure media is watching, etc. But at the time I wrote this, yeah, it was probably much more reflective of where I was in my personal life. At the time, it didn't seem to matter that it was a random roll because I kind of wanted to leave enough gaps for the player and their own conception of love. And I was less interested in all the complexity involved in our weird decision-making around things like that, right? That's not to say, though, that there aren't more theoretical, more sound theoretical sort of basis for, of varying levels of robustness for how love and romantic partnership might work and how we should model those things and select partners. From the sort of fluffy end of the spectrum, there's an exercise suggested by Susan Quillam of the School of Life, who wrote the book How to Choose a Partner, where she suggests there's this matching up of top 3 values across 3 different axes of what makes living worthwhile and achievements and personality traits. Effectively, you kind of end up with this matrix of 9 values. She doesn't quite say what you do next when you have those 9 values, but I assume you build a social simulation game where you generate a host of characters, each with a different one of those 9 values, and see what happens if you try and match them up. That's probably not what most people do. Or you can just list those 9 values on Tinder or something. Or another theory that's more mathematically grounded, which you might be familiar with, proposed by John Billingham in this old 2008 article he wrote called Kissing the Frog, A Mathematician's Guide to Dating, is that it's best to discard the first 37% of whoever you come along and date, and then pick whoever is the next best one after the first 37%. And Dr. Hannah Fry, actually, she wrote a book as well called something like The Mathematics of Love, where she suggests that obviously there's lots of problems with that theory, right? Because how do you assess whether or not the next person who comes along who's marginally better is better enough, or maybe there'll be someone else after that. So, you know, because you can't look forward, right? So anyway, there's all these different possible models. But in Red Shirt, I went with randomness. So, which I think, like, since then has kind of remained with me, because I'd have loved to have gotten to a more robust theory of love and relationships and how I should have modeled them. This is what the interface for Red Shirt looked like at the time. Because it meant, I mean, not only because it would have been interesting to try and get to that, but also because there would have been more to expose to the player, right? There would have been something that I can say about this as a theory of how relationships work. So in a way, though, the lack of a particularly deep model for how the mechanics of people and feelings worked in Red Shirt didn't matter too much, because Red Shirt was ultimately a game about it wasn't really about deeply exploring one relationship. It was more about seeing people as disposable in a kind of way. Don't get me wrong, though, because I actually had lots of players write to me, write to me with various things that happened in their games about the sort of arc of their characters and relationships that came and went. There was one player who had his in-game girlfriend dump him for the boss that they both mutually worked for, who was like really lecherous and flirty. And then after he left, he left that job because he was too upset. So he got another job and got promoted up the ranks there, found someone else to settle down with. And then the original girlfriend basically came back and started spamming him with lots of messages, insisting they get back together. And so the player did, and then just sort of died, coupled but miserable. So that's Red Shirt. So one of the things I do want to point to is how, if we do, on the flip side again, if we do use randomness in these systems, it kind of gives us a get-out clause, right? So when we're obviously creating these generative systems and stories driven entirely by agents, we can obviously see the machine itself as a co-creator, someone else who's there with us doing a part of the expression beyond just the creator, us, and the player. So we can kind of rely on this sort of third participant to contribute to it equally with whatever it's decided to be the most appropriate. And so that effectively gives us this kind of useful distancing. It can be useful to us personally by allowing us to kind of rescind ownership of a particular model that we built in our games. So I could have been like, okay, this is a model of how love works, but no, when in practice, this isn't actually what I'm saying, it's actually the computer making these decisions. And maybe we can do that because it's too personal or too controversial or otherwise. But again, the flip side of that distancing is that it allows us to pass things off with a kind of objectivity which isn't actually there. So, oh, there we go. Just put a little artistic creator hat on the computer. So, with some of the early computer art movement, specifically, so a lot of the work of the male practitioners working in that tradition, there was this kind of attempt at self-distancing through maths. So this is Gaussian Quadratic, which was a piece by Michael Knoll, which kind of tried to foreground the relationship between maths and art. And Michael Knoll actually tried to copyright this, and you might be aware of this story. He tried to copyright this multiple times, but it was actually rejected repeatedly on the grounds that a computer had generated it, and that it was random. And so he went back and forth multiple times, and it was only when he admitted that a human had actually defined the combinations of order and randomness, and that it was actually a piece of human expression, that he was actually allowed to copyright it, and the copyright was granted. So a lot of practitioners in this way, this is just one example, specifically wanted to distance themselves from their art. And so the abstract world of math combined with the autonomous nature of the machine was what distanced them. But at the same time, wider public perception, particularly in the early days of sort of generative work, was that computers are these cold, soulless machines anyway, creating these cold and soulless artifacts. So this is a quote from Jean Hayes Beeman, who's one of the early pioneers of computer dance and choreography in the 60s. And she talked about the ways in which sort of generative work was thought of, right? So there was this uniformly dismissive message, thought of as these sort of capitalistic, soulless machines, the sort of sign of the very thing that artists were trying to emancipate themselves from. And some of her work was actually featured at the 1968 exhibition Cybernetic Serendipity, which I always love bringing up because it's such a weird and wonderful exhibition which seemed to sort of come out of nowhere for its time. And it was kind of the first ever celebration in the world of generative machine art. It was held in London at the Institute of Contemporary Art, and it was basically designed to promote the work of these pioneering artists who were using the computer to respond to, or building various machines to respond to external inputs in some way from people or the environment and react accordingly, often in unforeseen ways. You know, the word, well, the title itself, Cybernetic Serendipity, is a really nice one. And there were plenty of women whose work was displayed. It was actually curated by Jassia Reichart, which I'm not sure if this video is going to play. It's quite long, I'm not going to play the whole thing, but gives you... Is there any sound? Oh, hang on. Let me just switch my audio.
Or who have written the poetry are artists or poets or composers. In this exhibition, in the first section, we have works which are produced with a cybernetic device, with a computer. That is, computer-composed and played music, computer-generated graphics, and computer texts and poems.
There's a bit which I really like, actually. Is it coming up? So there's a wall of just sort of generative... Oh, here we go. Is this the bit... It's a word of... There's a wall of just generated words. It's not this one, there's another one, and it just kind of prints out the word poop over and over again.
What
oh, here we go. There it is.
In this particular particular work was to take letters, which consist
I love the slow zoom.
circles, semicircles, and straight lines. And this is why you get letters like P and L and O. And what he did was to try and find what words would make sense using these components.
Okay, so this gives you a sense of the kind of work that was being displayed there. And there were a lot of, and so the late 60s and early 70s were full of women working on generative computer art. So this is Lillian Schwartz together with one of her pieces on the top. And in a way, it was because the field of the emerging field of computer art at the time was one which no one seemed to quite own yet, right? So it was a place which felt up for grabs, as Anne Spelter said. So in those early years, social norms seemed more fluid and gender barriers remained unconstructed, even though computing would masculinize soon after. So that's kind of a side note because I was kind of talking about distancing and randomness. And randomness isn't kind of always, it's not always bad, right? So, like I said, all of that is besides the main point because as someone who is building systems for social models of things like love or people, etc., it offers an opportunity to reflect upon how that phenomenon works. But of course, there are multiple ways that we can interrogate social models. So zooming back out of all of that, so I am broadly interested in procedural character-based narratives, right? And even that, I think you can sort of conceive of having sort of being this spectrum of agent-driven stories on this end through to story-driven agents on the other end. So I just want to sort of set up some definitions and sort of what I mean by that and the way it works. So agent-driven stories are those which are based around obviously simulating the interactions of lots of agents, and it can tell us something, there we go, it can tell us something about that particular world through obviously having the player interrogate and interact with the social model that underpins those agents. And the way that we tell stories there is by really through a mechanism of noticing, right? Noticing the difference between the ways that different agents behave and the way that they're set up in opposition to each other. So which ones are different from each other? Why are those particular differences so? Like what properties do they each have? And why does that matter in the context of the particular world? So again, agent-driven stories rely on lots of agents, and the storytelling comes from noticing. So yes, you might notice the green dot. Okay, I've added animations, which I totally forgot about, but there we go. So yeah, so you can see that this is not moving and the others are, so that's how you might know. On the other hand, there are what I would call story-driven agents. So these are agents which have been crafted to know a lot about a particular story space. And the way that you learn about the story space is by interacting with that particular agent through dialogue or some other set of interactions which act upon them in some way, right? So yeah, in this one, it's about kind of going deep on that particular agent and finding out about their agenda and what makes them tick. So at Spirit AI, which is the company that Julian mentioned, we're working on the sort of story-driven agents side of the spectrum. So effectively, we're sort of a tools and middleware company, and we developed two products. One is called Ally, and that's sort of more off in the area of online harassment detection and intervention. But the other one is called Character Engine, and effectively, it's an SDK and a set of tools for helping you create characters who you can have a conversation with. They'll respond dynamically. They'll keep track of what you've what you've talked about so far with them. What routes the conversation has gone down, and they will sort of effectively improvise based on the particular sort of narrative space or pool that they have. And they can draw dynamically from those. And they can also, these characters that you create can also respond with regards to how they're feeling emotionally at the time. So if as a player you've been kind of mean repeatedly, then the particular responses from the character might be kind of annoyed. They might just sort of tell you different things altogether, and so on. Maybe they'll emphasize different words. So the point is that that these characters are more deeply expressive, right? So they can say things about the narrative space that they live in, which a narrative designer or a writer has specifically crafted. And they'll tell you those things through the lens of however they're feeling, and be able to understand and respond to a wide range of expressive input as well from the player. So I will try and do a live demo, which is always a bad idea. But so the particular demo that we have, this is the character in that demo, which is about interrogating a robot who has been taken into custody for some kind of crime and is able to improvise off of both a set of examples of scripted dialogue that you've defined for it as the writer. So it has kind of an agenda that it follows, but then there's also, and I'll talk a bit more about this in a second, there's also a deeper, there's a knowledge model, right? So a kind of structured database of information which it can pull out and then do some text, generate some text from. So yeah, again, the point is that if you as the player have treated the character in a particular way, or you've developed a particular relationship with them over the course of a scene or over a longer game, or even if this is in some kind of pervasive game like an MMO or something, that character will effectively sort of treat you through the lens of its relationship with you. I'll show you. Oh, so this is just a screenshot of the authoring tool that that we've built to basically craft these scenes and build these characters. I won't go too much into depth on this, but if anyone wants to ask about it afterwards, please do come up. So I'll go ahead and show the demo. I just want to show you a flavor of what the system is like. So let me just switch over. Okay, full screen. Okay, just let this get going. So there is dynamic voiceover.
I see they have sent additional investigators to collect data on Martin's murder. Hello.
So the things we output are effectively, what the thing is that the character is saying, and also their current emotional state, right? So in the top right-hand corner, in this demo, we've just output what the emotional state is, right? And it sort of ties into some light animations, but kind of that's really not the point. So don't pay too much attention to what's going on visually. You'll see that she'll shift around, but that's kind of, obviously the point is that a game developer can tie that into their own animations, etc. So she's opened with one possible sort of greeting, right? So she's got, and this will be kind of different, sort of different every time. So she's got a few different ways that she can say, effectively say hello and welcome you to the scene. So I'm going to go ahead, again, live demo. I'm just going to say hi and greet her as well.
I hope you'll have more luck than the others unraveling this murder.
We know that we're interrogating this robot. We know that there's been a murder. We don't know anything else about it. So I can go ahead and ask her, like, anything about the murder at all, or anything about what she's doing there. I'll say, who was murdered?
The victim, Martin Hastor, was hit in the head with a blunt instrument once, hard enough to kill and produce a great deal of blood. It does not appear to have been a prolonged beating.
Okay, so she's got into some gruesome detail there already. So to find out more, I'm going to just say, so who was Martin? And so this information that she's giving, that she's relaying to us, actually all of this is coming out of the structured database that I mentioned. So she's got a database of facts, and she's pulling those out and forming those into phrases, into sentences. So, for example, she says, she opens with the victim, Martin Heister. If she's mentioned Martin to us before, if we came across this later, she might have just said Martin or he, etc. So so I'm going to say who was Martin.
Martin did leading robotic research that fed into Valtruck's most profitable sales.
Okay, so, and again, this is all stuff that she's telling us from the knowledge model that's coming out of the structured database. She's still calm as well, so we can kind of start messing with her a bit now and see what happens. I'm going to ask her a completely different type of question, because so far I'm asking her about like facts and things. So I'm going to say, are you guilty?
Where the murder is concerned, the person who wielded the blunt instrument is guilty, though there might be an accessory. I'm unaware of such a person.
So we can see that she is still calm. She's getting a bit shy now because we've addressed the concept of guilt. So what I'm going to do is, and so she also will respond to sort of positional information. So I'm going to lean forward, so I'm like leaning up against her, leaning up right in her face across the desk, and I'm going to say, I'm going to ask her again, are you guilty?
Where the murder is concerned,
see she's repeating her answer, but now she's getting more anxious.
Is guilty, though there might be an accessory. I'm unaware of such a person.
And if we did, sometimes if you're sort of repeating something, she'll say, like I said, etc. So she'll kind of contextualize it a bit. So I'm going to say, I don't believe you.
Please don't hurt me. I'll answer anything you want.
Okay, so now she's getting arrogant and really anxious. I'm going to say, actually, no, I'm going to not keep being mean to her, because I know that from past experience, I know that she, and the way that the story works, she will stop talking to you if she gets too anxious. So what I'm going to do is try and calm her down. So I'm going to lean back out, and I'm going to say, I'm sorry.
Don't worry about it.
Okay, and so now she's happy. She's still a little bit anxious. We haven't really done much to relay the fact that we are very sorry. But so I'm going to keep talking to her about other stuff. So I know again from the story that she likes talking about her creator. So I might ask her, who created you?
Alicia is a valued researcher in behavioral AI. She created me, and she likes to upgrade me with new features.
So she's now calming down, so that's good. And again, most of this is being pulled out of the knowledge model. I'll show you an example, actually, of the way that the characters can make assessments of things like events in a timeline, like what happened before this, what happened after that. So, so I might say, what features?
My trainer, Dr. Alicia Chastain, made gradual changes to my programming that altered how I reacted to Martin, leading to a transgression in which he kissed me.
Okay, so she's talking about a particular event that happened, right? This like transgression. So I'm going to say like what happened after that, and then
after the murder, my encounter with Sergei in the loading dock happened.
Okay, I'm going to say what happened. She's getting anxious now. She's coming across the murder, so I'm going to say what happened next.
After my encounter with Sergei in the loading dock, the data loss happened.
Okay, so she's getting really anxious, right? So I'm not going to overload it too much, but that gives you a flavor of how the system works, right? So I'm going to just quit that. And this is only a very short demo. And best make sure I close. Okay, so. All right. Okay, so you can see that that very much adheres to this kind of idea of really going deep on a character, right? Trying to sort of explore their particular agenda, explore the things they know about, the things they care about. So it's all about sort of foregrounding one character and allowing us to go deep on them. And I think that's really interesting because it gets us closest to the ways in which we can possibly understand each other, right? I think I've become a lot more interested in sort of this idea of like, how do we really get at sort of models of human behavior? Really, it's by talking to each other, right? We don't have these direct feeds into each other's brains. All we have are cues from each other, verbal cues and non-verbal cues as well, language and the words we use, which are a really big part of that. So this also kind of points to the way that the two ends of this spectrum that I've defined between agent-driven stories and story-driven agents actually kind of shift the locus of who's responsible for putting that model together. Because the two types of character-based, of procedural character-based narratives affect writers and designers in different ways. With the former, with something like Redshirt, it's up to obviously the programmer or the technical designer or whoever is laying out the sort of systemic social model to define how people work. It's up to us basically as engineers to dissect and work out things like how do people work and how do feelings work and how should we model feelings. But on the other side, so with something that like what I just showed you with story-driven agents, the shift moves towards writers and narrative designers to model the inner life of a character through language. So again, it points to how language is super important. And again, it is a spectrum. So another game that I've been working on the past couple of years, which I will finish at some point, tries to sort of be at a midpoint on that spectrum. So this is the trailer for it, but it's called Little Invasion Tales, which is a sort of quirky city building citizen management game where you're trying to manage both citizens and build buildings, etc. But it hinges on these sort of quirky emergent occurrences amongst the cast of socially simulated citizens. And the occurrences which the system deems to be the most interesting are narrated in real time through voiceover. And then some of those events are selected for kind of an end-of-game summary for the player, complete with screenshots and a sort of comic book retrospective, which they can see. So because, again, speaking of language, one of the missions that I'm trying to accomplish with Little Invasion Tales is bringing a wider, maybe more ostensibly casual audience into the fold of understanding procedural narratives and sort of, what basically happens, because all of the players' interactions with the world are converted to sort of narrated story text through voiceover. So again, it points to how procedural characters need to be expressive about their world. And that's kind of the challenge with Little Invasion Tales, because in Redshirt, it was kind of an easier problem because the world space was basically just what you could see. It was like other characters and what they were doing and so on. So it was basically procedural characters in a kind of vacuum. However, in Little Invasion Tales, there's kind of other things going on as well besides the characters, which they need to be able to comment on. The goals that I had for Little Invasion Tales was, again, this idea of having, allowing for quirky emergent occurrences between the citizens. Things that are the most interesting should be the ones that are narrated. And there should be sort of remixing of these displayed script lines. And again, the most interesting should be displayed at the end for a kind of retrospective. And again, these are all ways that the procedural characters should be expressive about their world. So the expressivity here is displayed through these means. I'm not going to get into this here because I did, together with Alan Hinchcliffe, my collaborator on this, a AI Summit talk at GDC this year about how this worked, which was basically a modified goal-oriented action planner together with a rule-based query system. the query system was also the foundation for sort of the dynamic story generation system, and the thing that did the sort of the scoring and filtering and grouping of events. But yes, if you want to find out more about that and how these are sort of two separate but interdependent systems, you can have a look on the GDC Vault. So hopefully all of that underscores that it is a spectrum, and what I tried to do with Little Invasion Tales was kind of be somewhere along that spectrum, right? So again, lots of agents working sort of juxtaposed with each other, but then also hinged around sort of a story that's explicitly being told. But on that point, I'm also really interested in what can we come up with when we bring both sides of the spectrum together? What kind of procedural character-driven narratives might be possible then? So let's just sort of, almost bend the ends of the spectrum and just sort of merge them, right, into a big circle. Because then the way that the meaning making would potentially work is in both ways, right? You get kind of the best of both worlds. We get to juxtapose agents with each other, noticing the difference between them, but then you can also interrogate any given one deeper as well. Again, merging these two concepts, seeing how a particular agent works differently from another, and then going in and finding out more about them. An example that I always like to point to is imagine if something like Papers, Please was such that you could really sort of like have a conversation. What if you could talk to the characters more deeply, right, and find out about their motivations and interrogate them? I guess I've got 15 minutes or so left, so I'll start wrapping up so there's time for questions. Yeah, I think that's actually I don't need to say that, I've said that already, so thank you.
Thanks for this excellent talk, Mita. We have time for questions, indeed. So,
Hi.
Hi.
Is this on? Yeah. How you deal with in this kind of conversational agents that you just show in the demo?
Yeah.
How you deal with unexpected questions from the user, talking about topics that actually have nothing to do, or misspelling some words or whatever? How do you deal with those?
Yeah, so there's a few different ways. I mean, so the misspellings point is a separate point which I'll come to in a second. But in terms of just input which is seemingly random, like if I ask the robot what's the price of coconuts or something, right? That's kind of an authoring point, right? So you can sort of say, okay, if the player is asking something about a topic that I don't know about, then this is the kind of here are some example responses which might be given, but you can still filter it through it's like some kind of sentiment. So is it a question to begin with, right? So you can see if it's a question, but maybe it's a question you don't know anything about, but you can still say, you could set it up so the character asks you more about it, right? Like, oh, did you mean this, for example? Or you could see, so effectively the way it works is when there is a piece of input from a player, it goes through several, I forget what the number is, but several different classifiers, right? So yeah, we have lots of information essentially about what it is you're saying. So it's kind of an authoring point, what piece of that you want to use, right? If that answers your question. Okay.
Hello. I would like to ask you if is this demo available to be tried?
Not just yet, no. So this is a demo. It's actually it's the one demo that we've been kind of showing publicly. We had it at GDC. We are working towards something that we can put on like our website, etc., or share videos of it. But it's not available publicly yet. But you can come and interact with it afterwards if you want to.
Okay. Thank you very much.
You were mentioning knowledge fact database,
yes,
where you store all this background information, knowledge. What kind of database is it? So is it more like a probabilistic database or some sort of logic program, or what kind of formalism do you use for that?
Yeah, I mean, it's basically, so let me show you the authoring tool that might be, might answer a lot of these questions. So, if I open this up. Okay, okay. So yes, this is the authoring tool. So there are two sources of information. So this is the sort of knowledge, the knowledge model. So effectively, it is just a data. So there's a few different types of entities that are sort of baked into the system. So things like topics, people, events, but then you can sort of add other entity types that the character might know about or care about. So in this particular story, she knows about the concept of conclusions. She knows about the concept of places. She knows about the concept of institutions. And then you can also assign different types of fields. And again, these are completely customizable. So in here, we've said, okay, again, there are some baked in ones which are in bold, but something like the concept of goals is one that's just been added. And you can say, or even, something like age, and age is, it's a int or a number. And you can sort of say, okay, well, institutions have ages, conclusions don't have ages, etc. Right? So that's the way that works. So yeah, I don't want to sort of go into it too deep. Oh, this is the event timeline. So this is kind of where you can add information. Add specific events like we asked about. So that's where you'd say, okay, what happened before this? What happened after that? How long after this did this happen, etc.
You're using this authoring tool to build this knowledge base. And I'm wondering if we could write an algorithm and like process some events, some news from an event. I mean, for instance, I've been to the 9/11 memorial.
Yeah.
If we fed the news and information into this timeline and everything, so we could ask questions about that.
Yeah, we've actually done some prototyping of that with just an XML feed of sports scores from like
and the bot behaved like.
And you can just ask questions about about that particular event that it now knows about. So there was a different character. It wasn't this bot.
But the algorithm was the same.
So it's basically just storing it in taking in an XML feed, storing it in the format of the knowledge model, which is just XML. So yeah.
Thanks.
Hi. Mido, what is the kind of information you have on types, the effect of type of events, emotional effect of types of events? Say things in the story that can make you sad, angry, tired, fed up, and so forth.
How do you mean?
How do you author this, and how do you determine what are the effects on the character that certain types of events in the story have had?
Oh, I see. Okay. So there's a few ways that can work. So again, this is all made easy in the authoring tool. So for example, so you can sort of say, okay, if the player's sort of input context is such that they're being angry, right? They've said something which is kind of mean or whatever, then the response, the sort of performance that comes back from the character will be to set their sort of emotional state to this thing, for example, right? So there's a few ways that this can work. I'm trying to find a good example of this. And again, so these, well, just to sort of give you some context, so this is, these are just sort of examples of sort of input context from the player. So if the player says something like, who accused you? So this is a context, which is, okay, they've said this with this, it's a question that we recognized, it's about guilt, it's about the robot's identity, the performance that they'll return is, they'll say things like that with all these different variants, and then also they, we can say that this will happen when they have this particular trait active, etc. When they're, when they're angry, etc. And these are all emotions that I don't know if right now you can define them, but eventually you'll be able to sort of add custom emotional states as well. So, any other questions?
So I thought of, okay,
yeah.
we still do have time. So basically, I mean, I know that this is, and sorry, I've seen the system before. I know that part of the point of this is to break free from the traditional sort of mode of interaction in adventure games, role-playing games, so you essentially have dialogue trees and you can explore them. And basically, if you play, Zelda or Skyrim or whatever, if you want to sort of get further in the story, the thing to do is to talk to all the people and ask all the questions and say all the things, and eventually you'll have exhaustively explored the conversation space, and that will progress you in the story. And many of us maybe do that. That's how we play things, such as Mass Effect or whatever. I'm not sure I'm proud I actually got the achievement completionist in Mass Effect 2. This is sort of wanting to change that model completely and have a different type of interaction, which I think is fantastic. But how do you then control the difficulty of progressing in the game? Because, I mean, what you're showing here is a way of doing exploration. But what about progression? How can you sort of how can you make sure that an average player such as me would eventually sort of progress in the game?
I mean, that really depends on how you've incorporated the character into the scene, right? So it could be a scene about, okay, you have to get this character, in order to progress, you have to just get this character angry. It doesn't matter how you do it. You just have to get them angry, right? So, and then once you've done that, once that trait has been activated in the character, then you can progress. Yeah. For example.
So then you basically can. So then you're still doing sort of exploration, but in another space, you're exploring the feeling space.
Yeah, it's true. Exploring the feeling space.
That's true. Yeah. Yeah. It just strikes me as there's a lot of interesting challenges in trying to automatically set and judge this difficulty. I mean, a lot of the work on sort of level generation goes on, and game generation is trying to address the difficulty problem and the challenge problem by doing automatic playtesting and so on. Could you see this being combined with automatic playtesting, for example?
Yeah, so, well, one of the things that we are working on, and again, all credit to, so Emily Short is actually the product manager for this particular side of what we're doing, and, you all know her work, she's amazing. One of the things that is coming is an addition to the sort of authoring tool where we sort of have an easier way to read in sort of like a whole bunch of player logs and sort of add in any sort of content that we've sort of missed, or here are particular things that players tend to be asking about the most. We should probably write, more content for this piece, and just lots of handy visualizations for narrative designers to be able to take just player data and and enhance the character.
Cool. And when you say authoring, so let me just continue by asking the question from the other Julian, the one that isn't here to help game designers, but to replace them. Right. So could you get past the authoring? Could you automate that part as well, and automatically create these sort of? I
mean, I'm gonna be careful with what I say because
you're in a live stream.
because well, I mean, one of the things that we're explicitly underscoring all the time when we go in to talk to studios is this is not about replacing you, right? This is about helping you be more creative and do more, and generate more types of variation in things that characters can do and say and behave from the things you've written, right? So that's my diplomatic answer.
It's great.
The other thing I wanted to add, so obviously I'm talking about my sort of interest in. So why conversation is like kind of an interesting mode of interaction and finding out and exploring social models. There are a lot of people who are interested in systems like this, and people that we're working with who are using this in kind of VR contexts, right? So the input being speech to text, and then doing the rest of the kind of processing you've seen here. And even we had an earlier version of this which was designed for like pre-GDC this was, which was set up in Vive, so you could actually like walk around the robot kind of in room scale, and she would respond to kind of where you're standing and comment on if you're sort of facing away from her or like if you're looking at a wall while you're talking to her, etc. So currently we're sort of improving the sort of speech to text capability, so we're not sort of running that demo right now, but and there's a lot of people sort of, that we're working with who are interested in that kind of VR application. But I think, rather than it being about believability per se, because we were talking about this on the panel yesterday, right? Is the ultimate goal these sort of really naturalistic characters who kind of reach towards, like the idea of virtual humans? I think that is interesting. But I think that just the idea of conversation alone is just a really interesting mode of interaction. But then believability is important as well. So my doctoral work was looking at how sort of things like VR affect believability, right? Affect the way that we process what we're doing to characters and how we're interacting with them. So, yeah.
Right. And with that, I think we've reached coffee.
Okay.
So let's thank Mito again. Excellent speech.
Thank you.
Next session starts at 11, General Video Game AI.
Hi.
We're going to have a lot of time to entertain you in the next couple of weeks.
Oh, cool.
But first question for now.
Yes.
Are you? Oh.
I know. Yeah, I did that. It was fine.
Apple and coffee. Are you maintaining somehow the consistency between the feeling moods?
Hello, everyone. We're starting the next session, last day of the conference. This session is called General Video Game AI Playing. I am Gabriela Barros, and I'm chairing it. Let's all welcome the first speaker. The paper is called Rolling Horizon Evolution Enhancements in General Video Game Playing. And the speaker is Raluca Gaina.
Close enough. Hello, and thank you for the introduction. My name is Raluca Gaina, and I am an IGI student from the University of Essex. And today we'll be talking about some experiments we did playing around with Rolling Horizon evolutionary algorithms in general video game playing, and some modifications we tried to boost the performance of this algorithm. This domain has been dominated for a long time by Monte Carlo research, but in the context of the general video game AI competition, it has been shown that the Rolling Horizon evolution does show some promise of matching and even surpassing the performance of MZTS. We have two other papers that are published in similar areas of Rolling Horizon. I should not touch cables. If you want to learn more, there will be a link at the end for my website where you can check it out. But in this particular study, we focused on some modifications in previous literature that have been explored in various contexts and in various parameter settings. So we wanted to bring them in general video game playing and also give them a consistent environment to test them, see if they work and if they work well together as well. When we are talking about game playing AI, it's usually one agent that is able to play a particular game, like Go. A lot of people just immediately go to that these days. But there are also a lot of researchers taking interest in StarCraft, and the AI is getting better and better in these games. But these agents do incorporate a lot of domain knowledge, and they spend a lot of time training on these particular games. And if you took them and asked them to play a car racing game, for example, they would just probably crash the car the first chance they got. So what would be more interesting and what our group is focusing on is general video game playing. So getting one agent that is able to play several games and even unseen games that it's never seen before, it's never been trained on, but it is able to adapt to these new scenarios. And this can, of course, have some applications in the game industry and even the real world, with removing the need to come up with new tools for every project you're starting. You can just get some general ones. Or for game testing, currently you'd have to employ several testers to see if the game you created works in the way you intended, and if it's easy or hard. So instead, you could take one or a bunch of these general agents with different behaviors and analyze how they do, and at a much lower cost. And to that extent, we are working in the general video game AI competition, which has been previously covered briefly, so I will not go into much detail, but we are focused on the single-player planning track, and in particular the 2D grid physics games, which there are about 100 in the framework at the moment. And these games vary in many ways, from the options for the player to interact with the environment, to the scoring systems in the games, and what makes games end. But all they actually get to know about the games is a very high-level overview of the current game state. They only get to know that there's an object in this game. They don't know what it does, what happens if I go and interact with him, so they have to figure this out, and they have only 40 milliseconds of thinking time to actually make decisions. In this domain, we apply the Rolling Horizon evolutionary algorithm, and I will try to highlight the parts of this algorithm that we addressed in this study as I go and explain it. So it first starts with a population of individuals that is randomly initialized at every game tick, and this first step is actually the first part that we addressed, which we called population management. These individuals battle it out in a tournament, and 2 of them are selected for crossover, where each individual represents a sequence of actions to be executed in the game. Then we apply a uniform crossover in the vanilla version of the algorithm. So we're selecting random genes from each of the individual and combining them to form a new one. And then we are mutating this individual by selecting one random action and replacing it with a new random action. This is the second part that we are addressing in this study, the mutation operator. Then we have to evaluate this individual to see if the sequence of actions that we obtained is actually any good or not. So in order to evaluate it, we take the actions in turn, we put them through a for model that simulates the game state that we would get to if you were to apply this action in the actual game. And once we get to the end of the sequence, we evaluate the final state through a heuristic that gives us a value representing how good the sequence of actions actually is, and that becomes the fitness of the individual. This evaluation part is the third that we will be addressing, the individual evaluation. And finally, the process is repeated for all the individuals in the population, except for the first one that is promoted directly through elitism. And at the end of all the generations simulated, we will select the first action of the best individual to actually play in the game. And that is the last part that we are concerned with, and that is the action recommendation policy. And for a brief overview, so we'll be looking at mutation operators, population management, action recommendation policy, and individual evaluation. We'll be looking at this in isolation as well as combined to see if they form some interesting things together. But because there are so many combinations between them, and we also looked at different parameter configurations, we split this into two parts, where we looked at the first three first, and then we added the individual evaluation to the best algorithms in the first part of the experiment. We tested each algorithm on 20 of the games in the GVGA framework, and with different core parameter configurations. So the first enhancement that we looked at is the mutation operator. And for this, we replaced the random mutation that we had before with a UCB-based mutation that we called EA bandit. And for this, we have two layers of bandits, first at individual level, which selects which gene to mutate next. And then we have lower level bandits for each particular gene that decides which action should be chosen. And for this, we use the UCB equation that basically balances between exploitation of good actions and exploration of possibly good actions. Then we have population management. For this, we looked at a shift buffer, and we call this EA shift. The idea is to retain information between game ticks. So we spend all of this limited time that we already have, and we go through a whole process of evolution. And in the vanilla version, we would throw all this away and start fresh with a new sequence of actions from the next game tick. But with this one, we choose to remove the first actions of all the individuals in the population and just add a new random one at the end. So we're still keeping that information and try to evolve on top of it. Then we have the action recommendation policy. This is keeping a statistical tree alongside the evolution. We call this EA tree. And the idea is that when you evaluate an individual, you keep all of the actions that you go through in a tree. And over time, you accumulate that information. You get to understand more about how useful an action actually is. And at the end of the evolutionary process, we use this statistical tree to recommend the action as the most visited at the top level of the tree. This is different to Monte Carlo tree search because the statistical tree is only used for statistics. It's not used to guide the search in any way. So we only use it at the end to see which action is actually better. And finally, we have the individual evaluation. Normally, we would go through the sequence of actions, and that game state that we finally reach would be evaluated to see what happened. But in this version, that Vanessa might know some more about as well, we apply some random rollouts at the end of the sequence of individuals. And this would increase our search horizon a bit, but in a more dynamic way. So we don't have a specific set of actions that we will go through. We are randomly sampling and trying to increase that look ahead. And the length of these simulations we chose in this experiment was half of the length of the individual. For the actual experiment, we tested 4 different configurations for each of the algorithms to see how the population size and the individual length actually impact these specific enhancements. All the other parameters are fixed to some default values, which I won't go into detail about. The budget was set to 900 calls of the form model, so 900 simulations of what happens next in the game. We chose to do this instead of the 40 milliseconds in the competition because it would be machine independent, so we wouldn't have to worry about fluctuations on the machine we ran the experiments on. And 900 is the average that the vanilla version of the algorithm achieves in the 40 milliseconds in the actual competition. So in the first part of the experiments, we looked at the first 3, the EA Bandit, EA Tree, and EA Shift, plus all of their hybrids and their combinations together. In the second part of the experiment, some spoilers, don't mind those, we took the best algorithms from the first part, which turned out to be EA Tree and EA Shift, and we added to those EA Roll. And finally, we validated against MCTS to see if this is actually any good, and we are achieving our purpose of beating this algorithm. For the games that we selected, we chose 2 classifications in the literature that rank the games depending on the performance of Monte Carlo tree search or various other agents in the competition. And we randomly sampled from this, which would give us a nice distribution of game difficulty in our game set. And we ended up with 10 stochastic and 10 deterministic games of varying difficulty and game type. And these are just 4 of the games that we ended up with. Aliens has been briefly described before, and you might recognize Missile Command as well as a classic game. For results, the shift buffer enhancement, so the one that preserves information between game ticks, turned out to be the best one, while the bandit mutation was the worst. We actually observed a performance proportional to the parameter values that we've seen before in our studies. This was not very surprising. But one thing that was interesting was that the shift buffer enhancement manages to perform a lot better than the best vanilla algorithm in its low configurations. And the low configurations means that you get to do more generations, more evolution. So with this algorithm already being a lot better than the vanilla version, it means that there's a lot of space to improve the evolutionary process and get even better performance. And we have here a heat map which shows the number of significant games in which the row algorithm was better than the column. So the darker the color, the more games there are. And the way to read this is basically looking at the rows for the best algorithms and the columns for the worst algorithms. The darker the column, the worse the algorithm. And we can observe that algorithms A and B, which are vanilla and EA shift, stand out as the best rows. And for the columns, we also notice that F and H, which are EA bandit shift and EA bandit tree shift, they stand out as the worst. And to go quickly through each of them in particular, we have first EA bandit, which turned out to be the worst variant. And this was mostly because our individuals in the population are sequences of actions. And due to this, when you change one action in the individual, the rest of the actions change their meaning. So for example, if you have an up and then following a path through the level, if you change that up to a down and you follow the same path through the level, you would end up in a different place. So that is one of the issues with this system. Our bandit system only looked at genes as individuals and not as the sequence of actions that we were interested in. So that would be an interesting thing to improve. then the EA tree turned out to be the best in the lower configurations. And that is mostly because with more time to do more generations with the lower configurations, then we would get more information to add to our tree, and the information would become more accurate about what's actually good in the game. So that does make sense. And our EA shift turned out to be the best variant, with achieving higher scores in most of the games, significantly higher. And its worst hybrids were with the bandit mutation. For the second part of our experiments, we looked at adding these simulations at the end of the individuals. And the best algorithm turned out to be the EA shift role, which is combining the information retention between game ticks with the rollouts at the end of the individuals. The rollouts turn out to be the most advantageous in low configurations, which means that given that we are already offering some part of our limited budget to these rollouts to perform some more look ahead, it does make sense that we can do more in lower configurations, so we get more information and more benefit out of them. All of the variants turned out to be better with rollouts than without them, except for the tree search. It turned out to actually be worse to keep the statistical tree next to these rollouts. And finally, we performed a validation against Monte Carlo tree search. We looked at the best algorithm and the one that is most similar to MCTS out of our selection. So the best algorithm achieves for the first time something that we've been looking for, and that is to match the generality of Monte Carlo tree search. In our previous work, we have obtained better performance than MCTS, but that would be in a specific set of games. The performance would only increase there. In this work, we have managed to match the generality, which is measured in the GVGAI competition by Formula 1 points, which is basically a way to normalize the scores. So an agent that scores very well in one game and very poorly in all the others should not be better than another agent that achieves an average performance in most of the games. And then we looked at the algorithm most similar to MCTS, which is EA tree roll, the one that keeps the statistical tree, as well as doing the simulations at the end of the individuals. And this turned out to actually be significantly worse than MCTS, but it still is better in puzzle games. So to conclude, our bandit system did not work because of this idea that sequences of actions have a different meaning that the system was not able to handle. The statistical tree turned out to be most beneficial in lower configurations, while the shift buffer increased the scores that the agents were able to achieve in the games quite significantly. Then we also saw that the shift buffer with the rollout enhancements saw an increase in performance inversely proportional to the individual length. So the more rollouts we could do, the better. And our best algorithm was the EA shift roll with a configuration of population size 10, individual length 14, and 5 repetitions of the simulations, which manages to match the MCTS generality. And for future work, we will be looking at meta-heuristics, so a way to dynamically adapt these algorithms and decide which one we actually want to use at the problem at hand. Because even though we did get an algorithm that seems to be more general and get good performance, there are some that perform better in certain scenarios. So it would be great to switch to those in specific situations. We might look into bandit mutation and improve that to actually handle the idea of sequences of actions and not just look at them individually. And we would also like to explore more games to better judge significance. We do have 100 of them to look at, and the number is growing. Thank you.
So now we open for questions. Please come here if you have any questions.
Oh, no, there's a queue.
So you said that you used uniform crossover in the vanilla version. Did the other versions also use vanilla crossover or crossover at all? I was unclear on that.
Crossover was uniform in all of the variants, yes.
So I think that that could also be introducing a problem because of the same issue with the bandit. Because if you arbitrarily mix actions, then you destroy the action sequence. Yeah. And so if you did a single point crossover, then anything that's beneficial on the left side would be retained, and you'd only be varying what happens after that. So I mean, just exploring different kinds of crossover, I think also would be a way of improving this.
Yeah, that's a very good idea, and we'll definitely look into that. This was mainly exploring things that have been done previously in literature, so we played around with those, but it's definitely a very good point.
There are a lot of unusual forms of crossover that are maybe less well known, but there's tons of variants, and I think that there are some that are specifically designed for sequences of actions, and so if you search deep enough, you should be able to find them.
Yeah, thank you. Yeah. I'll definitely look into that.
Hi. That's a cool animation, by the way.
Thank you.
Very distracting as well. So I think it was a really good idea to try to have a set of games that are as diverse as possible, right, by doing this characterization stuff. But I was wondering how many of the games were actually like how many of the games where the agents were actually able to play something, like where there's meaningful, because you in the VGA competition you got lots of games where either all of them win or none of them do anything.
That was definitely one thing that we did take into account when we selected the games. So we did try to look at games where something actually happened and they did manage to win sometimes or get some kind of score. But there are a couple of games that we thought we should include at the bottom of this ranking because maybe some kind of enhancement combination would perform actually and manage to break out of this non-win scenario. But that is a minority of our game sets. In most of the games, they actually did stuff.
So that worked?
Yeah.
Were there some games that were...
There were some games that did go from 0 to something. That's not much, but something.
Right, thanks.
So that was cool. Thank you.
Thank you.
I was thinking about the shift variant, and it did really well. You tested it, and it's because it's saving a lot of work that you've already done evolving, right? So if the population is evolving towards something that's a good solution to the game, absolutely. Are there games where there are strategic local optima and using the shift variant could drop you into a local optima and get you stuck?
That is possible. And one of the things that we did try with this shift buffer as well was to introduce some information loss. So we would try to forget about things that we've learned after a certain time so that we do try to avoid this and introduce new things into the population, get out of that.
Okay, you're already on top of it.
Yeah, thank you.
So it's cool work, and I'm happy to see that this really works. And we, yes. With Ivan Bravi, we tried something a little bit similar. Also the shift thing, it didn't get it to work. We never submitted it. We sort of went into a different direction after that.
Okay.
But so I wonder about the bandit mutation. It seems that it didn't quite work, and I understand that mutating sequences is action sequence is a tricky thing. What was the reasoning behind it? Why would it work?
The UCB one.
Yeah, the bandit-based mutation.
It was mainly based on work that Jolene and Simon have done before that used this bandit mutation in a random mutation hill climber. That is slightly different to what they did, but we did think, hey, why not try it out, see if it actually works.
But the bandit would reset for every new run of the evolution.
Yes.
Or for every generation even.
It wouldn't be for every generation.
No, but for every generation.
Yes.
Is it maybe just that 900 function evaluation is too little for it to work?
That is very possible, yes. We've not tried it. So.
I think just to clarify with the bandit. So the version of the bandit that we used in this paper was an old version of the bandit, so it wasn't the entable bandit. And regarding the small number of evaluations, that's one of the reasons to use a bandit approach to get the sort of maximum benefit of what you're sampling. And I think one of the next things we need to try is with the full entable bandit that we haven't tried yet, which does take the epistasis into account. And then the other thing about that is that we need a proper shifting bandit that works with a shift buffer.
Yeah, definitely.
So I think with those enhancements, I expect it to work, and we'll have to wait and see.
Yeah.
But shifty bandit, yeah.
Okay, let's thank our speaker one more time.
Thank you.
And our next speaker is Cristina Guerrero Romero. The paper is called Beyond Playing to Win, Diversifying Heuristics for GVG AI.
Hi. Hi, everyone. Hi, Internet. I'm Cristina Guerrero Romero, and I'm a PhD student in the IG program. And I'm going to present my first step in my research, which is diversifying heuristics for GVGI. So to give context to everyone, my research is focused, or the idea is use the general video game agents for evaluation and create a system capable of evaluating levels and games without having any kind of prior knowledge about them, and creating a pool of agents with different goals and different different ways to go through the levels and the games to be able to understand and know how to learn and play the games, and then give feedback to whoever is creating the levels, or if it's a PCG or it's a designer or whatever. So it's a big PhD, but I have to start somewhere, so I decided to start trying different agents that are already available, developed by different authors, and create different heuristics, not focus on winning. There has been authors that has been tried different heuristics, but they usually were focused on like improve a certain algorithm, or improve how to analyze a level, or how to make agents win. But so what I wanted to do is forget winning. Well, one of the heuristics is winning, but trying the agents to do different things, like explore or discover different elements in the game. So what I did is surprise using the GVGA framework. At this point, if in the conference you have heard about this for sure, so I'm not going to get into detail, and Raluca has given a little bit of GVGI everything, so I'm not going to get into detail. And so I'm going to just start with what I did in the experiment. So basically, I took 20 games from the framework, and the selection was done based on previous work from other authors, and then I created 4 different heuristics and took 5 of the controllers that are in the framework as well. Then for each of the heuristics, I ran each of the controllers 20 times in each of the 20 games, in one level of each of the 20 games, based on their performance, following a certain criteria for the heuristic, rank them to see if in all the cases the same agents perform the same or there are differences depending on the heuristics, and so I can, it gives me a general idea so I can start somewhere with the research. So to rank the controllers, we use the F1 ranking system because it's a fair way to evaluate how to benchmark the agents. And then we compare the rankings and made some analysis based on on how the agents perform and some stats for each of the heuristics. So the 5 controllers we took for the experiment are the one-step look ahead, which is one of the most basic algorithms available in the framework, apart from random, but that doesn't count. And then we choose 3 search-based algorithms, which are OLEDs and open loop MCTS, and then 2 evolutionary algorithms, which is the rolling horizon and random search. And I'm not going to get into detail on the algorithms because it could take me the whole talk. So in the paper, they are briefly explained and they are referenced. So if you want to know about them, just check it. So I just mentioned that I updated when I took the algorithm from the framework, I had to do some common ground modifications to have a fair comparison between them. So what I did is, when it was possible, set the depth of the algorithms to 10. Then I extract the evaluation functions from the algorithms to have them outside the algorithms, so I could easily plug in different heuristics on them without having to change the actual code. So that way I was sure that the comparison of the heuristics, what we wanted to do, was fair. And then I implemented a cumulative reward in the forward model, because for some of the heuristics I needed to keep track of what was going on in the forward model as well, and have some info, and in the algorithms it was not possible to have that, so I needed to include it. So the 4 heuristics we developed was winning, exploration, knowledge discovery, and knowledge estimation. And I'm going to go through each of them and the rankings and everything. So the winning is the basic one, and is the one that most of the agents in the framework follow, and it's very simple. So the agents just focus on winning, and if it's not possible to win, they maximize a score. A demo of these heuristics, if it loads. Yeah, this is the Butterflies. It's one of the games in the framework, and the goal is basically the fairy has to take all the butterflies before the time runs out or the cocoons are open, and the cocoons are open when the butterflies collide with them. And in this case, this is random search using the heuristic, and as you could see, it won. And the criteria, so these are the rankings. In this table, I display the order of the controllers by the points after the results, and then on the other column, in the average % of wins, that is some criteria, some stats that we thought it was important to check for each of the heuristics as well. So first, for the criteria to evaluate the performance of the algorithms for these heuristics, it was taken the number of wins for each of the controllers in each of the levels of each of the games. And then if the best controller is the one with the most number of wins. After that, if there is a tie, it's considered the higher average score. And if there is a tie in that also, it is considered the agent that in average took less time to win the game. And that is how the ranking of the F1 points were calculated. And then for the stats that are over all the games, we can see that Olets, which is the first one as well, he has an average of 59% of average of wins, which is very low. It's high, but it's not perfect, obviously, because there are 40% of times that he didn't win. So the second heuristic is the exploration one. And basically in this heuristic, what the agents were focusing, it was on maximizing the positions visited in the levels. And this heuristic is very simple. It was based on a matrix. And with visited or not visited positions. And every time an agent visited a new position, it was marked as visited, and if it not, it was not. So it aims to visit as many positions as possible. This is the same game played by an agent following these heuristics, and you can see the behavior is different. It basically ignores the butterfly, they don't really care, and just try to move around and visit as much as possible. So the criteria followed to rank the performance of these agents with this heuristic. It was the percent of the level explored, which was because the framework doesn't provide information about how much is the how many positions are available to explore. We had to do this manually and extract for each of the levels and the games we took, like the positions that were available, and to be able to start a valid percentage. So that is the criteria, and if the percentage was the same, because in some of the cases, some of the agents were capable of exploring 100% of the level, the second criteria followed to perform to check the performance is the agent that it took less time to explore the level. And so in this case, a random search is the agent with perform better. Even when in the stats, we can show that OLEDs has a slightly higher average of percentage explore over all the games, but it is not that different, but that is, so yeah, I'm going to go to this one. This is the knowledge discovery heuristic. In this case, the interest of the agent, it was to interact with the game as much as possible to trigger different sprite spawns and interactions. So in this case, what the heuristic wanted to do is acknowledging different elements and try to interact with the game as much as possible. And if it has interact with all the elements that are available, try to interact with as much as possible in different locations of the game, which we call curiosity. And for this heuristic, we created a knowledge database with the sprites of the game and interaction table, which is the interaction between the avatar or between different sprites in the game. And we have to distinguish between collision and action onto. I will define this. The collision is when the avatar collide with another sprite. In the previous example, in the butterflies, for example, is the avatar, the fairy colliding with the butterfly. That will be a collision. And the action onto, because in the framework, it is possible to create agents that shoot things and generate sprites because of shooting. So if the fairy was able to shoot something like stars or something, if the stars collide with the butterflies, that will be an action onto interaction. So we distinguish between these to be able to make different stats and check the performance. In this case, this is the agent following the heuristic. So as you can see, it moves through he likes the trees because instead of trying to move in around empty spaces, it's trying to interact with the trees as much as possible or with the butterflies. And the behavior is different as well. And the criteria follow to, one sec. Yeah. In this case, was the number of sprites capable of acknowledged by the agent. If this was the same, the unique interactions with the agent with elements in the game, and if that there is a tie in there as well, the number of curiosity discovered, which is the number of different interaction in different places of the agent during the game, and in the and we had to define a lot of things, but it doesn't usually go farther than 3. But the other 3 criteria was the agent that with less average game tick, acknowledging the sprites, the last unique interaction, or the last curiosity discovery. In this case, random search was the agent with best performance as well, and related with the stats. In this case, it was not possible to have like a overall because of the sprites in the games are different. It has to be like a relative stat. So instead of being able to consider in this game, this agent discovered 2, in the other one discovered 5, because the number is different, it has to be like a relative comparison. So it was considered the agent that acknowledged the maximum number of sprites was taken as reference for the other agents in this stat. So that is why there is a 100% in random search. That doesn't mean that he acknowledged all the sprites in all the games, which will be amazing, but it's not the case. The thing is that he discovered the most number of sprites in all the games in relation with the other algorithms. The last heuristics was the knowledge estimation one, which is based a little bit in the same idea of the previous one, but instead of trying to interact with, it interacts, but the idea is trying to predict what happens after those interactions. So if you interact with a sprite, will I win? Will I lose? Will nothing happen? How many points will I receive? So the idea is interacting, and that is why in this agent use the forward model to acquire the knowledge, and not only in the real time what he achieves. So at the end of the game, the knowledge he acquired is used to try to predict what happened in each of the interactions. So in this case, instead of using curiosity, what the heuristics is trying to do is trying to interact with the game uniformly to be able to have as much knowledge as possible of every sprite and not just one certain sprite. In this case, if I can go to the... Okay, no, you will have to watch all of it. It doesn't behave as same as the previous one because it moves much less, because it just really don't try to move all around the map, but it moves more randomly or stay in the same position, like in this case. So, and at the end of the video, if it finishes, because I cannot, well, a little bit more, it will appear like the predictions, and there are 2 sprites in this case. The agent collides with the tree, which is the sprite 0, and the butterfly, which is the sprite 5, and the trees. I don't know if you can see it, but in this case, this is the win estimation. So when the agent collides with the tree, it doesn't estimate anything, and it estimates that the score of colliding with the tree is 0.00, which is fine because the tree doesn't give you points. And in this case, with the butterfly, the win estimation is a little bit higher than 0, because there are some cases when it encounters a win, because when you collides with all the butterflies, it will win. So in some forward model, he discovered that. And the score estimation is 2, which is the real score estimation in this case. I need to speed up a little bit. So the criteria, it was the smallest average of the prediction square error in these estimations. And in this case, the open loop MCTS is the one who performed better. And this is another screenshot of the different behaviors in another game, which is clear that the agents the same agent with different jurisdiction behave differently. So that is good news because it can be used for different things, and I could use this for my research. This is a comparison of the rankings, and it is clear that the performance of the agents depends on the heuristic used. So there is no an agent that wins in every case or an agent that performs bad in all of the cases, because, for example, the rolling horizon doesn't perform good in this case in the winning or exploration, but when in knowledge it performs much better. So it's a clear difference. Another thing to notice is that for the 3 first heuristics, the difference between the first and the last algorithms in the points is very noticeable. But for the knowledge estimation, there are only 47 difference, so it's much more uniform, the performance of the agents. So to conclude, this is like a possibility to enlarge GBGP techniques. So instead of just trying to improve algorithms, it could be research how heuristics affect those algorithms and maybe solve at some point this problem. And obviously, it's very challenging and difficult to have an agent performing well in all the games, even when the heuristic change, because obviously it's general and it's a challenging research. And the future work, the idea is improve the heuristics, combine them maybe, you repeat this experiment using more levels, using more games to see how the different games the agents perform, the heuristics perform, to analyze what can we do or in which games, which heuristics work better, which works worst. Maybe applying this idea to the learning track that is new, because maybe it's the logic follow-up, and hopefully in 3 years have GBGI to evaluate like levels and games. So thank you.
So we have time for 3 or so questions. If you want to, I would like to invite the next speaker to start setting up.
Okay, this is interesting, nice, and I think there's definitely a lot to be done here.
Yeah.
And I think it's fascinating that random search actually was the best explorer here. But which points to that, there's you have a lot of good. I mean, this is good work to get started with, and there's lots of good work left to do, definitely. So just, you've seen Christopher Holmgård's work on procedural personas?
Yes.
Yeah. So we've been thinking about like expanding this to the general case, but we never done it. Would you say that this is a way of doing procedural personas in the general case?
I'm not really, I know his work, but I'm not really familiar with human behavior algorithms.
Human behavior is pretty tricky.
Yeah, so I don't know.
No, but basically he is also trying to get. So this is all done in one particular game, which was constructed or designed specifically for this reason, where you're basically trying to find like different heuristics that sort of create almost maximally different ways of playing the game. So it's also compared with humans, but it's like
I thought it was like more compared than that.
Yeah, but basically it's almost the same. So it could be interesting, and maybe you could even use some of the same methods we use to compare with humans here in this case.
Okay, yeah, I will definitely check it more. Thank you.
Yeah, it's good work.
So just curious, where did you get the motivation heuristics? How did you come up with them? And are you using stuff like Quantic Foundry or game design research to like come up with these personas?
There is some authors that look into these heuristics before, but just to improve like MCTS or other algorithms. So I decided to use their ideas and see how they will work. So, and because I thought they were really, really interesting and...
No, they cover a good spectrum. I was just curious where they were coming from.
So yeah, based in previous work, and then I took the idea from them. The references are in the paper, so you are curious, you can check it.
Right.
So you mentioned that during the interaction with objects in the game, then you consider, for example, all the scores or the score change is considered. So maybe I didn't get it, but how do you handle some kind of delayed scoring or delayed rewards? Is this considered in these kinds of heuristics?
No, in this heuristic is very simple. It just check the difference of a score. So it's something very simple. Yeah. It's not. There are other authors that have done winning heuristic, like more complicated, but in this case it was the simplest one. Yeah.
Thanks.
No worries.
Let's thank our speaker one more time. The next speaker is Ilhan. The talk is called Monte Carlo Research with Temporal Difference Learning for General Video Game Playing.
Hello everyone, I'm Ercüment İlhan. I'm a master's student from Istanbul Technical University. Now I'm going to present to you our work, Monte Carlo Research with Temporal Difference Learning for General Video Game Playing. As the title suggests, in this paper we have attempted to enhance Monte Carlo Research with temporal difference learning method to make it perform better in general video game playing domain. The presentation will follow this outline. I will first give some background information, then I will define the problem, then I'll explain the proposed method, and then I will share our experiments results, then I will conclude with some future work. Okay, so some background information. As you know, general video game playing is a problem where you're trying to design an agent that can play multiple different games without being programmed for one particular game. And most recently, there was a framework developed for this problem. It's General Video Game AI framework, and it also has a competition. It's based on video game description language, and at the time we made this paper, there were more than 90 games in it. And also right now it has 5 competition tracks. The main focus of this research is single player planning track, and I'll talk about it. In this track, you need to design an agent, and it will get evaluated in a set of 5 hidden games. at the start of every game, you get 1 second to initialize your controller, then you get 40 milliseconds at every game step to decide on an action. You can train your controller previously, and between every game, your controller is getting resetted, so you can't share knowledge between games. However, a forward model is provided, therefore just you can plan ahead. What's provided to our agent in these games are the game grid with the items and the types of them, and the game score, game tick, win-loss status. However, you don't get win conditions, scoring conditions, and results of interaction between items. You have to find them out on your own. This competition is held since 2014, and when analyzed, we can see that one of the most successful baseline approaches is Monte Carlo tree search. It's being a core of many winner controllers as well. Therefore, I am skipping this, as we all know how it works. So what we are trying to improve here, as I said, in general video game AI single player planning tag, they give you 40 milliseconds at each game step. Therefore, Monte Carlo tree search algorithm is also modified to reflect this. So its rollout depths are limited to prevent it going all the way down, because the games can take up to 2000 steps. In that limited time, if you don't limit rollout depth, it can't do many of them, and therefore can't evaluate tree nodes successfully. However, making this modification also as a consequence, which is you have to add a custom node evaluation method, because you aren't reaching a terminal state. You can't just back up win or loss result. And this is the most basic one of them. When it is an intermediate state, it just backs up game score provided by the game. And if it's a terminal state, it's also enhanced by a high value or low value, depending on if it's win or loss. What kind of problems are in this approach? Because in this approach, the agent with limited rollout has a limited sight, so it sometimes can't reach a rewarding point at the map. And also, because we rely on game score, no matter how close it gets to a reward, the state score doesn't change. It's always 0, and when you get a reward, it's 1, let's say. Therefore, this evaluation method doesn't provide enough feedback, and also a small number of rollouts. This sample Monte Carlo tree search also follows uniformly random rollouts. They also don't provide enough information when the number is low. There has been many research in this algorithm, including pathfinding methods, evolution algorithms, multi-objective methods. However, there have only been a few modifications that involve reinforcement learning methods. I think there was one last year which enhanced knowledge-based Monte Carlo tree search with Q-learning. And in this work, we attempt to enhance the base one with a different reinforcement learning method. And now I'm going to explain you what we did. As I said, we need a custom state evaluation method and custom rollout policy for more efficient evaluation. If we can treat rollouts as Markov decision process episodes, like experiences, these two tasks turn into prediction and control problems. As first, we are trying to predict a value of a state, intermediate state, and after that, by using these values, we are trying to drive a better policy to direct the rollouts. And in the literature, there are two well-known algorithms. One of them is Q-learning, other one is SARSA. Q-learning is known for its off-policy control nature, and SARSA is an on-policy algorithm. As it is said to be have better convergence, we have followed SARSA in this research, and we have also employed a recently developed variant of it through online SARSA Lambda. It's said to outperform all TD Lambda variations. Okay, so in reinforcement learning methods, you are trying to learn a value of states. However, you can't just have a table of every possible state and learn the values of them. So therefore, you have to use function approximation. And in this one, we have used linear function approximation. So according to this, we extract a set of features from every state, and we have weights associated to these features that are subject to learning procedure. We have followed the very basic feature extraction method. I will show you here. This is the game of butterflies. At the initialization phase, we first analyze how many item types in the game, which is 4 in this case, and we then build a dictionary with combinations of this. We got 6 here. Then at every game step, we compute minimum Euclidean distances between all these. Then we turn them into proximities by subtracting from 1. And then we take element-wise squares. I will explain this. This is our state representation. And about rollout policy, we want to direct the agent to the promising points in the game state, but we still want to explore the game. Therefore, we use the well-known epsilon greedy policy here. With epsilon probability, it takes a uniform random action, and otherwise it takes best action suggested by the algorithm through online SARSA Lambda with highest value action. And the third modification we did in the algorithm, the Monte Carlo tree search, is the backups in the rollouts now involve discount factors. I will now illustrate this process. This is the vanilla Monte Carlo tree search. It goes down with uniform random policy. It obtains the game score in the final state, and it backs it up. In our version, we go down with epsilon greedy policy. We obtain transition rewards. We evaluate the final states, and in the final, we back this up by multiplying them with discount factor because the learning algorithm has it in itself. If we don't do this, we can't evaluate different levels of tree fairly. Now I'll show you some experiments. We did our experiments in 2 different sets. Actually, the second set isn't included in the paper. We did it after. In the first set, it's CIG2014 set. It has 10 different games with 5 levels, and it's same with the second. To evaluate, we played every level 100 times, which makes 500 plays for each game. Oops. Yeah. And another thing we did is, since we are making these tests across different machines, we were getting inconsistent results. So we changed the time limit into a fixed number of rollouts at every step, which is 50 for vanilla Monte Carlo tree search across the first set of games. This provides consistency, but may not reflect actual behavior of the algorithms at some points. And we compare 3 controllers. First one is vanilla Monte Carlo tree search. It's also included in the framework. The other one is our algorithm. We have determined these parameters empirically. There are 4. And finally, we test the same algorithm with half number of rollouts because we know that learning process needs some time to, and there's a trade-off between number of rollouts and learning process. I will show you tables, show you graphs, and the table I will start from here first. As you can see, these are the 10 games in the CIG training set. We did statistical significance tests between these algorithms. We have combined our 2 methods with vanilla one, and you can see if it's significantly worse, better, or significantly better on the next of them. As we can see, TD MCTS is better than better than vanilla Monte Carlo tree search in 3 of the games significantly, and also it has it improved the overall win percentage by 25%. And in the average scores, there is actually no clear winner. They all get similar average scores. And these are the graph form. As we can see, in 3 of the games, this method has provided a clear edge over vanilla Monte Carlo tree search. However, on the other ones, they are quite the same. And also, this is the validation set. In this one, the results are much better. Like in 4 of the games, the proposed method is much better than vanilla Monte Carlo tree search. And these are the scores. We actually didn't analyze the scores much. We were more focused on the win percentages. Conclusions. As we've seen, reinforcement learning can indeed enhance Monte Carlo tree search and give us some advantage. However, state representation is a really critical part. We followed the really basic one here. It was too basic, actually. It was simple, easy to learn. However, it didn't provide any directions. And it's bad when you are trying to select actions by control. And for the future work, I can say these algorithms have large parameter sets, and they are quite hard to tune and across all games because every game needs different parameters at different values. So developing a game adaptive method could be really helpful. As I said, state representation method could be much better. And trade-off between learning and extra rollouts wasn't analyzed much in this research. It could also be improved, I think. That's all. I can take questions if you want.
So as you said, I mean, the improvements were much better in some games than others, and in some games there even seemed to be like actually made it worse.
Yeah.
But if you looked at, what really stands out is the camel race. Camel race is sort of an edge case. It's not really a game. It's just a way of tricking MCTS essentially. Because for those who don't know, camel race is a game which can be won by going left.
Yeah.
And that's it. Pressing one button for a long enough time. So why would you think that the TD learning enhancement made it so much better for this game particularly?
Because, as I said, in the feature representation we have weights, and actually we did a trick. We started weights at 1 instead of 0 because by doing that, every object in the map has some curiosity effect.
Right.
So the agent could get close to them and try and see if it's a good or bad.
Okay.
That was why camel race.
Yeah.
It was.
Makes sense.
Yeah.
And for the other games where it did well, you had some in the test set as well, right?
Sorry.
And for the other games where it did well.
Yeah. This is the first set.
Yeah. So Missile Command, for example, I mean, it wouldn't seem to have the same learning benefits. So if you go to the other set,
first one.
Yeah. So why Missile Command? Because that doesn't seem to obviously benefit from learning to do a particular thing. I'm just like curious about what's it actually learning here.
Like in which one?
Missile Command.
Missile Command. In that one. Actually, I think it learned like getting close to planes, like hitting them were giving us a point, right?
Mm-hmm.
So yeah, because this is learning is reward driven, killing them actually benefits winning the game too. So by following reward giving sections of the map, it gone next to them, and Monte Carlo tree search, being close to them, could kill them.
Okay, so what it learns there is being close to the missiles.
Yeah,
is good for you.
Yeah, being close to the planes coming down.
All right.
That benefits the score.
So I'm curious to know if you compared your work with similar work applying TD to MCTS in this domain. You mentioned that there was one in CIG last year. Actually, it's one by my group, actually. So did you compare your method with?
No, I haven't.
Okay. So you haven't done yet?
Yeah, I haven't done yet, yeah.
Okay, so if you are interested in obtaining source code, and you can contact me.
Okay, thank you.
Sorry, I was kind of curious. Frogs and the other series, there's only two games where 25 TD MCTS 25 does better than 50.
Okay.
Is there a reason for this? In most others.
It may be because of that. As it take less number of rollouts, we use same learning rate across all controllers. By doing less rollouts, it's actually like if the one with 50 rollouts over learning something, the 25 one doesn't do that. That may be the case. Like I haven't analyzed that, but I am thinking of that. Like if you
the reason is what's in that game that makes it happen only on Frogs and on the other.
Which one?
Can you show the other series?
Okay.
Firestorms.
Firestorms.
And are the only two games where this happens?
I don't know about Firestorms, but in the Frogs, you are trying to reach a goal on the top. And I think as we start the way it's set 1, it's... Actually, I'm not quite sure about that because like I didn't watch the games it's playing. I'm just... putting some intuition.
Okay.
Yeah.
We do have time for one more question, but in any case, maybe the next speaker should set up.
Okay.
If we don't have any more questions, let's thank our speaker once more. Final talk of the session. We're almost at lunchtime. This paper is called Introducing Real-World Physics and Macro Actions to General Video Game AI, and Diego Perez is going to present it.
Thank you, Gabriel. Okay. So now to something completely different. Yeah. Yeah, okay, not really. Welcome. This is a project or a work done by a few different people from different places. Actually, 4 out of 5 are here. The only one that is not is Jochen, because he's in the other side of the world in Sky. And the idea is, as it says there, introducing new type of physics in the engine, and also explore what are the consequences of using this new type of physics in terms of the actions and the way that the agents navigate through the action space, and do a little experiment about that. I'm essentially going to talk about a small introduction about games that we have in GVGAI, the new physics that we have, the new games that are coming after this, and then different agents, macro actions, and experimental work. So I'm not going to explain for the 4th time what general video game AI is. I think it's already more or less known. In short, we want an agent or a group of agents that's able to play any game that is given. Now, I typically use this image, and it's good for explaining what's this general video game motivation about. But yeah, maybe you are thinking, well, you actually don't have a Pac-Man as cool as this one, or you don't have a Torx as cool as this one, or an actual Mario. Well, we're actually working into that. So we're trying to make the general video game AI framework be compatible with multiple different types of games, and at some point we want to have compatibility with this type of games, so more real games. And maybe one of the first steps is essentially what we are doing now. Just as a quick way of seeing how the framework works, essentially you have a game, you have a level, and that goes through an engine that creates 2 different entities. One is the game, the other one is the controller. And the idea is that the game starts, goes through game ticks until it ends. Competition setting, that's usually 2,000 game ticks, but that's only for the competition. You could really do whatever you want to do in your framework. And then the game communicates with the controller in a continuous way, so it's saying that every game tick gives information to the controller, and the controller just returns an action in, if possible, 40 milliseconds. There is some limitation about that, so if you go after 40 milliseconds, you would not apply any action, and if you go over 50 milliseconds, you would be disqualified. But the important thing is this real-time component that tries to require a continuous supply of actions from the controller into the game. Now, talking about games, all we have so far with what we have somehow called grid-based games is probably not very precise to say that they are grid games, because it's not like in all games one sprite has to occupy exactly one cell positions, but there are some discretizations that make this somehow constrained. So, for instance, the positions are discretized. You cannot be, or discretized. You cannot be in any particular point in the search space or in the level. Velocities are also not only discretized but also constant. You move at 0.1 squares per tick, then that's the speed that you have. All the sprites can be oriented, and with only 4 orientations: up, down, left, or right. So this implies some kind of limitations that we cannot have. It still is good enough. We have created 160 games between single player and 2-player, but we want to expand the amount of games, the type of game that we can create. And up to this point, there was no room for mass or inertia. The fact that you can move you need to apply more actions, consecutive actions to put something in movement or to stop it. Things like friction, gravity, or just simply being oriented in any angle with respect to the horizontal. That's something that it wasn't possible before. So the main idea was to introduce these new things into GVGI. Actually, this part of the work is mostly done by Matthew Stephenson, who's here, brought from his expertise with Angry Birds. So good guy to have on board. And the idea is to just modify the ontology to be able to have more fine-tuned movement. Velocity and orientations now can take any angle, so you can modify where are you looking, and not only in 4 particular directions. And there are concepts that are added to all the sprites in the game. One of them is mass, so you can add inertia to the active movement or the passive movement of a sprite. You can have friction, so when it's friction with the environment. So when a sprite is moving, you can minimize or dampen the speed that this sprite is carrying. So it basically would at some point stop if you add friction. And gravity as well. So basically gravity is a downward component which is added to the velocity of the sprite. If you define gravity, then it would basically fall. The ontology, in case you are interested in the code, at some point you can just check it, but there are new types of avatar, lander, that can give you a glimpse of what kind of game that we can create now, spaceship, cars, some kind of birds, you'll see what's that as well, platformer avatars. I think basically a type of different avatars that employ these concepts in a more in a particular layer. Again, new interactions, things that have been created for this, things like, well, for instance, wall bounce and bounce direction. So basically, when you had a sprite that was colliding horizontally with a wall, but we basically could change the orientation of the wall, basically going, if it was colliding towards the right, it would just bounce back towards the left. With bounce direction, we can just use angles. So you can, if you move diagonally, you can actually bounce in a more or less elastic way. And of course, new games. Just in order to entertain a little bit more the audience before lunch, these are some of the games that we have now. This is one called Artillery, which essentially allows this movement. You can see the rotation here of the avatar. The avatar now is somebody who is shooting some strange dog balls to. Wow! Oh dear. Yeah, that was a big explosion. And you can see also gravity here. Essentially, that was gravity falling. This is one called Bird that you might recognize, which is obviously using lots of gravity here. We don't have a scrolling yet, but at some point we might have a scrolling. Well, we can fake a scrolling actually. But yeah. We have one called Bubble, but actually you will recognize it as a clone of Pong. This is probably one of the most interesting games as I see with the new physics. You have nice collisions and also obviously the gravity as well. And I think I get killed here. Yeah. That's me playing, by the way. Lander, which is obviously a ripoff of Luna Lander. Probably we could have more nice effects, but it's gravity and also forces applying in rotation and acceleration. And we want to start having more platform-like games. There are still a few things to tweak, I believe, here, but you have a guy that jumps around in platforms, can kill enemies jumping on top of them, and at some point can get to the end of the level, which is like a mushroom or something. We can have Pong. This is not the most exciting Pong, because at the moment the other player just stays still. So it's kind of easy to beat. At some point the ball gets to the other end and you win. But of course, we can have 2-player version of Pong, and I think we have it already. So, good. Well, I shouldn't say it. It's secret. So we don't have 2-player version. Okay, so that's kind of the first part. We have a new space of games. Now, one of the things that happens when you add all these new elements is that essentially the search space has to be navigated differently, or actually the action space as well. So you sometimes need more precisions to move. For instance, when you are modifying the angle with the first game, the artillery one was shooting, you have many more degrees of rotation to how to actually shoot that. or when you are navigating a space where you have to apply many actions at the same time, each action is just going to add a little bit component to the velocity, and each action by itself is not going to modify too much the position and the actual game state. So navigation is going to be affected by all these things. And one of the things that we did in the past, back in the day when we were working with the physical travel settlement problem, maybe some of you remember that, the idea was to use macro actions for this. So essentially, instead of just saying each level of, for instance, MCTS, each level of the tree, instead of being only one action, that could be a repetition of 10 actions or L actions. I think actually here we're using M as the number of the length of the macro action. So that's M would be, if you repeat the same action M times, that would be the length of the macro actions. And the L, what we have here, that would be the number of steps, number of macro actions that you do in your sets. So just by using macro actions instead of actions, in the simplest form, which is just a repetition of the same action, we could see there in the PTSP that the improvement was actually massive, and it could work much better. And basically brings two different advantages. One of them is that you can do actually longer evaluations to the sidedness action. So that's a way to break the 40 millisecond rule. Because if you are, let's say that your M is 10, you essentially are saying, well, you decide an action of, or a macro action of 10 actions, 10 consecutive actions. That means that during those 40 times 10, or 400 milliseconds, you can start thinking of the next action that's going to happen. That assumes some determinism in the game. That might not be true. It was true for PTSP, it's not true for GVGI, but it basically gives more time to think to the agent. And the second advantage is actually reducing the search space of the actual algorithm in terms of how much can you look into the future, and how much you modify the actual game state as you move along. So in general, we can say that all the algorithms that we have tried in this small experimental setup, they have two different parameters, as I said. So L is the number of macro actions, and M is the length of each one of the macro actions. So we tried different agents. One of them is regeneration. I'm again not going to go through regeneration again. Quickly evolve a sequence of actions and try to keep the best one. I would just say that this regeneration that we have used here is the vanilla version. So it's not including all the enhancement that Raluca has been talking about before. And the other one, which I'm also not going to talk about, is Monte Carlo tree search. So again, tree search, balancing exploration, exploitation, grows very intelligently, is very nice. What I would say is that for both algorithms, you have a state evaluation at some point when you reach a state at the end of either the evaluation of the individual or the iteration of the Monte Carlo tree search. That evaluation is simple. You're basically considering the score of the game and plus a very big bonus if you win the game, or a minus very big bonus if you lose the game. So no heuristics in terms of knowledge of the games. So we have two algorithms. We have sorry, two algorithms. One is rolling horizon. We tried two different population sizes, so 1, 5, and 10, and Monte Carlo tree search. So that gives us 4 different configurations to play with, or 4 different algorithms to play with, and then 5 different look-aheads at tried. So basically, this is how far you see in the future, and then each one of these configurations is basically composed of these two LM. So in this case, that would be no macro actions because M is equals to 1. So that's basically a look ahead of 10, 30, 60, 90, and 120. So how many actions you see in the future. And then as you go to this part of the chart, you are combining. So that would be, for instance, doing 5 actions. Each one of them is a repetition of 6 times the same action. And that gives us the whole setting. Just the first one is the default setting. We want to compare this one as well. This is basically 10 moves ahead with single actions. That's the default MCTS that is in most cases, in most studies that use, and also the sample control is in the competition. We tried the 10 games that we have for this first training set with real physics, 5 levels, 20 repetition seats. So essentially, every agent is playing 1,000 games. Again, we use the trick to limit the number of forward models calls. So we don't want to specify or specifically wait for 40 milliseconds because that gives us the flexibility of not having to use the same machine for all the experiments, use a cluster and run many more experiments. And again, 900 forward model calls is an average that is more or less at the same level of the 40 milliseconds that every algorithm uses. Okay, so results come in many different forms. So starting with the first one, this is essentially taking all the games, you have seen some of them, with all the algorithms. And in general, this table basically shows that MCTS in their vanilla form is still working better in that rolling horizon in the same vanilla form. These results also offer an idea of how difficult it is to have different games or different games with different natures. So, for instance, this Angry Bird kind of game is basically not won by any agent at all, which is terrible. Or things like I think it's PTSP is only 4. This is the percentage of victories. So that would be none of them is able to win more than 4%. But the other games, for instance, well, Pong in this case, considering the bad agent, but still getting 70, and Racing, which is basically a game of moving around with a car and collecting icons or items, that gets about 50%. But yeah, it's very important, or at least noticeable, to see that there are 4 games, Bird, Lander, Mario, and PTSP, which are getting basically no victories. By the way, this is the default one. I didn't mention that. This is with no macration. This is how if you just launch the normal algorithms that we have directly to this set, what happens. Now with the configurations, we can observe many different things. This is all the configurations tried that use a longer look ahead and macro actions. And the first thing that we see at the moment is that if you see at the average, there could be the average number of victories, for instance, for MCTS in this configuration, in all games, across the 10 games. What we see is that in general, when you don't use macro actions, the average is actually better than when you start using macro actions. With short macro actions, is more or less stable, so it keeps at some point the quality of the results in some cases, but it's not exciting. And the population size for regeneration evolution actually matters. In general, longer populations or bigger populations actually work better. Okay. But before just saying, well, macration don't work, we can actually look at the different games. And it's also interesting to see that even in some cases, it's true that with no macration, everything works very well. When you start moving to macro actions of number 5, it's actually getting to work in some cases. But also more interestingly is that there are games like, again, another explosion. It's interesting to see that, for instance, Bird, which is a game that with no macro action is getting absolutely nothing, starts moving to 20 to 30% of victory. So there's a moment when macro action is actually, in some of the games, is actually helping. And actually, in all of them, Bird, Lander, Mario, and PTSP, the 4 I mentioned before, there is an increasement in the number of victories. For instance, Mario, that was getting 0%, moves to 20%, which is not great. It probably says that platform games need still more planning ahead. But well, without knowing that you're playing Mario, is definitely a clear performance improvement. After you saw a video about PTSP, I've been mentioning PTSP before. Essentially, what this game does is you manage this guy over here, and you move around trying to collect the green dots as fast as you can. And in this version of the game, there are enemies as well that you shouldn't touch. So this is an example when you don't have macro actions. You have a length of 30 actions ahead with single actions, and this is running narration with population 5, which is getting 13% of victories. So as you can see, basically every time that tries to move is just all the time navigating around the same area in the game. So sometimes, just by chance, probably because it's pushed by, I think it's going to happen here. So basically, this one pushes the agent in that direction, and that happens to be to just go and collect that particular agent. But in general, the range of movements of this agent is quite limited. I think it stays like this forever, so I'm just not going to continue. But with a configuration that gives you 6 actions, and each one of them with 5 different repetition 5 times of the same action, we bump from 13 to 50, and that essentially works much better. So it moves more around because it can cover more space simply. It's a very simple case, but it happens. And after a while, it just will go and collect this, the last one. Yeah. It's easier for them to move around. It's easy to navigate. And in this game in particular, it helped. In other games, it just didn't help. So just to conclude, we have expanded the game space that we can define with VGDL. We will continue within this during the following months. We have seen that no algorithm dominates any of the others, and that should be no surprise already. The previous 3 presentations have shown the same thing. So there is no algorithm that is better than anybody else. Somebody would try to remember freelance, but for that, we'll talk about it in the next paper of the session. We'll come back to GVGI with some freelance ideas. So I'll leave that for later. And macroaction in general, they are able to boost performance in some cases. Actually, in 4 of them, from no victories, we moved to actually being able to win the game. And in general, shorter macroactions require or provide better results. As future work, actually, one of the things that we want to do is to say, well, if some games are better with some specific macroaction length, then ideally we would like to automatically try to find which is the best macroaction for macroaction length for each particular game, which is not necessarily easy. We want to keep expanding the real world physics using continuous actions, the idea of, for instance, accelerate, full accelerate, or just mid accelerate. And also we'd like to see if we are able to apply this macroaction idea to grid physics. We have done some experiments. Actually, it's possible to win frogs with macroaction length of 5 almost 100% of the time, even if you just use the default MCTS, you'd never win. But these macroactions still need to be a little bit clever. It has to. They need to do things more convoluted, more complex than just repeating moving left for 10 times. But that's future work to do. That's it. Thank you.
Hi.
Hello.
Is it working? Yeah, it is. Well, first of all, I have kind of a short comment, if we have time, before my question. And well, given that it is you precisely who has been presenting this work here, and that some of your colleagues are here, I would like to say thank to you and all of your co-workers, and I think that in more general terms, your department and all the people, all of you who have been working so hard in this GVG AI platform, because I assume that you have been putting like a lot of effort and time in this, and I really, truly, honestly think that frameworks like this they are very, very important for the international community, both from the researcher and the teaching perspective. And I truly think that we need more things like this. So I just wanted to thank you for updating, improving constantly, and promoting and distributing these kind of tools.
Thank you.
Yeah. And the question. So these macro action sets, I guess that because under the future work bullet point, you said that yeah, you're planning to automatically find the best macro action sets. So I guess that currently these macro action sequences are like scripted or handwritten or something.
Yeah, it's just a variable that says the length of the repetition.
So the question is, according to your experience and expertise, what would you do? Where would you start to do this kind of automatical search of macro action sets?
I think there are different ways of doing it. Well, there are multiple ways of doing it. From the top of my head, I can think of 2. One is try to classify the type of game. So some games are going to be naturally more prone to be better with a longer macro action. So try to identify the type of game that you are in and say, well, for this, maybe navigational games or things where nothing is around me, maybe longer macro actions that allow you to move farther in the future. That could be a way to doing it. So first of all, classification of games. And the other thing could be a more dynamic way, because sometimes even if you classify a game, the game changes nature from mid-game over. So maybe at the beginning you just need to find a key that opens a door, and then after that moment the game is completely different and you have to kill enemies or whatever you want to do. So one thing could be classifying the games that are going to be to some kind of maybe a bandit algorithm, maybe something that tries different lengths and one of them at some point is going to be better than the other one. And probably that has to be some kind of window-based UCB or similar or thing that tries to say, well, at this moment, this length seems to be better than other ones. But it's not an easy way of finding this. It's complicated. Yeah. Thank you.
Diego, did you think of variable length macro actions, and when would that make sense?
I think it could make sense. So it can be done, I guess, in different ways. For instance, for MCTS, for every level, it's beneficial to have at least at the same level the same length for each, let's say, level of the tree. But it can be, and in some cases, it's probably necessary. Because there are games like Pac-Man where you have to maybe move 3 tiles to the left and then turn, and in some cases you're gonna have to move 5 times and then turn. So you might need in different moments different lengths. But how to define exactly at which point you use 3, at which point you use 5? That's that's more complicated. Yeah.
There's a rich literature in the RL community on options, which are a form of macro action. And then something interesting about them, there are methods for learning options, but the general definition of an option is that you have an entry set and an exit sort of condition. So it isn't that you're saying the action has a certain length. You're saying here are the states, or rather the properties of the states that can initiate the actions, and then here are the states, or rather the probability of exiting the action in these states is this value.
Okay.
And so you can define it in terms of what the agent, what state it's in, rather than in terms of some sort of variable length, which has its benefits. And like I said, there's a big literature on it. So.
Yeah, I've seen a few papers about options, and I think I agree. I think that could be something definitely worth looking into. Yeah. Okay. Well, thanks.
Okay, so let's wrap up. Let's thank our speaker again. And all the other speakers. It was a great session. It's time for lunch, people. See you back in the next session.